happy to see me.
Was she?
Baby. Mr. Baby. What did you eat while I was gone?
The tamales, beef,
Beef?
the ground beef.
Just all the leftovers?
Yeah, there's still some.
There's still some. Gross.
Excuse me.
Recording in progress. The heap property in a binary tree, right? It's like a row in between mass heap and min heap, and the fundamental structure for algorithms like this sort. Right? Simplify function ensure that the subtrees with the given node as the root satisfy the heap property, right? If the subtree violate the heap property, that's a lot of working and stuff. Let's actually do something easier for you guys. Okay, so in a nutshell, right? This is the final view, right? We have an array, and in this array is sorted, right? Whatever data in here is sorted. For example, in a mass heap, the data is sorted in descending order, right? In a min heap, it's going to be ascending, right? The other way around. And why we have mass heap or min heap? I remember the lesson on priority queue, right? Priority queue is something that it gets sorted, right? So we have some data structure that is sorted in order that every single time we insert a node in, right, it's sorted, right? So what is, let me ask you guys this question, why, what's the difference between a priority queue and a mass heap or min heap, right? So it looks like it doesn't have a lot of difference. But instead, the priority queue is built where you insert one node and you keep like, hey, insert another node, right? Insert it back, so it builds one by one, right? So imagine you have some array, right? It's like 1,000 elements, right? And in each of here, the data structure in here, the structure here can be an integer, right? Or double, or an object, right? And if we want to compare object, we know that we can overload operator, right? To compare object, right? We can do it. We compare different type of objects together, right? So this can be achieved by object overload, right? So long story short, so if you have 1,000 element here and it's not sorted, right? And you don't have a lot of memory, right? Don't have enough. Right, so this is all you have, and it's already stacked up like 1,000 elements in this space. Okay, what can you do? So this is great, right? So this is where the heap comes from. So the heap algorithm, right, allow us to do in-place sorting. So which means all we do in the whole time is just like swap the element, right? Between this, and swap it back and forth, swap it back and forth, swap these things back and forth, right? We don't use any extra element, this. So that's why this thing is powerful, right? And is that it's powerful because it's only using it swap the element, right? Using the same resource that we have. We swap the element together and make it sorted, right? So that's the difference between a priority queue, where we have one element, when we insert the other one, and over the time, right? One at a time, right? To build the priority queue, and the mass heap and the min heap is built by 1,000 or 2,000 or 1 million unsorted, right? And we don't even have the extra memory to handle this job. We just swap it and sort it. Okay, so that in a nutshell, that's the appetite for heap, right? Now let's go back to the element, right? The documentation, right? How this thing actually works. Okay, so we got the now we got a little bit understanding, like, hey, what the heapify function, right, and so on and so forth. And this is a step-by-step process to build a mass heap, right? Take a look at this. Okay, here's an array. The heapify can be used to build a mass heap by ensuring that its parent nodes is greater than or equal to its children. Fantastic. So easy to understand, right? So for example, this is the array. We have 3, 5, 1, 10, 2, 7, right? Unsorted. Okay. In step 1, show the array again. In step 2, it starts with the last non-leaf node. Okay, so now let's go back to one of the data structures we studied at the very beginning of the class, right? So not beginning of the class, but very beginning of the tree. So we have a tree, right? We call it binary tree. And the binary tree is like, okay, I have something like this, right? It's a binary tree. And it's not a binary search tree, it's not an AVL tree, right? So it doesn't care about the order of the right and the left, so it doesn't really matter. The only requirement is like this, right? It's gonna be structure like this. This is element A, B, C, D, and E, right? So let's put this thing on an array like this, A, B, C, D, and E, right? So in order for us to actually calculate the parent node on a leaf, right, we have a formula. The formula is going to be the floor of the index, right, which is -1 and divided by 2, okay? Floor of index -1 divided by 2. So sample 0, 1, 2, 3, and 4. Now we want to calculate which is the parent of E, right? So index number 4 -1, right? It's going to be 3. You divide by 2 is what? It's going to be 1.5. So the floor of 1.5 is 1. Okay, perfect. So let's check. Is it B? Is that correct? Okay, streamline is correct. So the parent is B. And obviously, 3 minus 1 is 2, divided by 2 is 1, right? So this thing is also correct. Okay, so this is the algorithm I want you to remember, right? In order to calculate the parent of node, right? You use the leaf node and you use the index of that -1 divided by 2. Okay, let's go back here. Right, that's everybody should be understanding, right? So start with the leaf node, index equal n divided by 2 plus 1 is blah 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 blah. Where n is the number of the element. Got it. Apply heap define on a sub-tree root at each non-leaf node from right to left. Okay, let's draw something over here real quick. Okay. So right now we've got a current trees like this: 3, 5, 1, 10, 2, and 7. Let's see up there. Let's do it again. 3, 5, 10, 2, and 7. Okay, so you apply heap define, the sub-tree root is non-node on the right to left, from right to left, so from 7. So we start at 7, right? Okay, so 7 start from index 2, value 1. Next step, 2, value 1. Compare 2 and 7 at index 5 and 7 is larger. Okay. So 7, right? At index number 5 is 1, 2, 3, 4. Okay, my bad. I missed the 0. 0, 1, 2, 3, 4, 5, right? And you compare, so the parent of 7 is 1, right? 7 is larger, so you swap 1 and 7. So you what? Swap. So you swap. And here, 1 go down, right? So compare. Swap 1, 7, and then the array gonna be 3, 5, 7, 10, 2, 4, 3, 5, 7, 10, 2, 1. Yeah, obviously. Then you move next to the next one, which is 2, right? And you say, hey, compare 2 to the parent is 5. So when you compare 2 to 5, right? 5 is bigger than 2, we keep the same thing. Then you compare 10 to 5, which is the next one in line, right? So now 5 is smaller than 10, so you swap 10 up here, right? Doesn't have to erase the picture. 10, 5, right? So then you move to the next one, right? With 7, 2, so 1, 2, 3. Then now you add 7 again, right? Because the first time you iterate, from this index like 5, 4, 3, right? You add right here, and then when you make a swap, now you add 7 because this thing is changing, right? So you add 7, which is right here, right? So now you compare 7 to the parent because 7 is bigger than 3, right? Swap 7 up here and 3 down here. Right? Then after 7, after this, you move to the next one, which is 10, and so same deal, you swap 7 down and 10 up.
I was like, and I took the shower cap off. I was like, oh
So
God,
down,
why do I
10
still
up,
smell
right?
like my dad's
And
house?
you get to the end of this.
It's my
right?
hair.
So once you hit to the end of this, right? You have something like this. 10, 7, 3, 5, 2, 8. Okay, 7, 3, 5, 2, 1. That's correct. Yeah. And then you swap 1 to the top, right? You swap 1 to the top and 10 to the bottom.
That's you.
1 to the top and 10 to the bottom. So swap 10 over here. And because 10 is the last one, right? So now you actually write 10 to the separate one. It's sorted, so it stays right here, right? And you actually want to remove it after, right? So you're gonna do iterate to this again, right? And when you keep doing that, you're gonna, the final one is gonna look like 10. Okay, keep doing that. Let's finish this actually. Then you go to the next one. First one down here is 2, right? So when you add 2, you compare to 2 to the parent of 2 is 7, right? So 7 is bigger than 2. You keep the same. You move to 5. Same deal. 5 is also smaller than 7. So you move to the next one is 3, right? So 3 and 1, because 3 is bigger than 1, so you want to put 3 up here, right? You swap 1 down here, so this thing becomes 1. Yeah, that's fine. Okay, so yeah, that's fine. So you want to swap 1 down here and 3 up here. 3 is going up, 1 going down, and you go to the next one is 7. Well, 7 is obviously bigger than 3, so you want to swap 3 down here, 7 up here. And you move to the next one is 7. So when you add 7, you swap 7 to the last one, right? And 7 is going down, and 2 is going down. The 2 is going here, and 7 is going down. Right? Because 7 is the next one largest. So, because when we hit here, right, we take 7 out here, right? Swap 2 and 7 is now separate. So you can literally like move out like this. Okay, and that's how you do it. So you put the next one, 5, parent 5, 3, right? Keep it the same. And now you go to XOS 1, and 1 to 2, 2 is bigger than 1, right? So it stay the same. Now 3, actually, my bad. 5 bigger than 3, so swap 5 back here and 3 down here. Five, 3, right? And then now we at 5, because 5 is bigger than 2, so 5 swap up here and 2 is going down. 5 and 2. So when we get 2, we go back one level. Now go to 5, right? We swap 5 and 3, regardless, right? Five is down here, and 3 is up here, right? When 5 is down here, right? Put 5 here, and we remove half these 3. Okay. So 2, 3, 1. So compare 1 to 3, 3 is bigger than 1, so it's the same. 2 to 3, 2 is also bigger than 3, so it's also stay the same, right? So now you swap 3 to 1, right? So 1 is going up here, and 3 is going down here. When 3 is going down here, we also roll 3 over here. And bam, you're going to have 1 and 2. 2 is bigger than 1, so 2 is going up here, 1 is going down here. Right? Now, because 2 is bigger than 1, so you want to move 2 down here. You swap 2 again, and you swap 1 to the root. Right? When you swap it, 2 after 3, and only 1 left. 2 is going here, and 1 is the only one, so you push here. Now it's sorted in a descending order, right? And when we have this thing, we call it a masking, right? Because it's sorted in a descending order. Now, right, I think this way is kind of confusing, right? There's one way to do it. There's another way to do it also. And in interview question, most likely they're going to ask you like this kind of question: hey, how can you build a PP5 function, right? And the logic of that, right? There are a couple ways to do it. You need to understand like how you build this tree first, in order for you to do this, right? Okay. Yeah, that's great. Okay. So now, instead of using like, let's see these 3, 5, 7, 2. Okay, now instead of using the tree, right? So now I'll demonstrate for you how you can using in-memory, right? So the formula should be floor and it's simple index, right? -1 divided by 2. It's also like 4. It's also add. This thing also work, right? These are the two functions that you can also apply for create to find the parent of a leaf node. So you have 0, 1, 2, 3, 4, 5, right? So recursive, we start 7. Now we start index number 5, right? So when we're at index number 5, we compare. I would love to do something like this first. So when we have 5, 4, 3, 2, 1, 0. Right? I love to calculate the 5 minus 1 is 4, divided by 2 is 2, right? And 4 minus 1 is 3, divided by 2 is going to be, yeah, 3 divided by 2, and get the floor is going to be 1. Then therefore 3 minus 1 is 2 divided by 2. So this thing is this thing. 2 and 1 is going to be 0. So this is going to help me to iterate faster when I'm doing this. So I'm at 5, and I want to see where's my parent. So initially it's like 5 is going to have a parent of 2, right? So 2 is 5. 3 and 4 is 1. And 0 is going to have, let's do something like this. Just think in color. 2 and 1. Okay? So that's about it. Now we can start. So if I take a look at 2, because 7 is bigger than 1, right? So we're going to swap. On the first run, we will grab 1 and 7. So we add here. Then move to the next one, we add 4, right? So compare 2 to 2. So 5 is bigger than 2, so that's correct. We don't need to change nothing. We want 2 over here, right? And then move to the next one, a 3, right? 10. So 10 compare 10 to 5, right? 10 is bigger than 5, so 10 is going here. 5 is going here. Over here, right? 2, 2, 1. And parent is 3, right? So currently, right now, we only swap 1 here, so the current value is 7, right? When you change it, you have to write down here. So 7 to 3, because 7 is bigger than 3, so you want to swap 7 to the top. And now, swap 3 right here. Okay? So now you go to the next one is 5, index 1. And the parent is 0. So now, 5, 0, 10 is bigger than 7. So you want to swap 7 and 10 to 2. So this is the power, right? In memory, remember, like we are in memory, we don't do nothing, right? We have using the sense, right? So now 10 and 1. 10 is go here. 1 is going here. Right? Swap 10 and 1. We have 7, 3, 5, 2. Okay? So, see that? Inside memory, we didn't change nothing. We only use the same space over. Okay, on the second iteration, we don't care about 10 anymore. 10 is done. It's done deal, right? So we start at 4. Right? Index number 4, we is 2. Compare 2 to the parent is 7. Right? It's good. Don't change nothing. Right? Okay, we here 2. Doesn't change nothing, right? And then we go to the next one is 5. So compare 5 to 7. It's good. Don't change nothing. What's the next one? A 3. 3 and 1. So 3 is actually at 2 right here, right? 3 is bigger than 1, so we'll swap 3 here, swap 1 here, right? And now we go to 7. Okay, so now 7 compared to 3, 7 is bigger than 3, so you want to swap 3 here, and now this is 7. Okay, back. Okay, so stand 10 is still here. We don't touch 10, right? So now 7, 2. Pretty cool, right? So swap 7 to the back, right? Swap 2 to the front. Okay, keep it. Okay, swap 2 to the front. 3, 1, 5, 10. Okay, so now same deal. We don't care about 10 and 7, they're done, right? Start with 5. Okay, so 5, compare 5 to 5. The trade parent is 5, a trade, so swap 5 trade, right? So trades go down here, 5 go down here, right? And same deal with the next one, which 1 is the child, 0. Perfect. Doesn't have to be 2 is bigger than 1, so keep them the same, so write 1 here. Move to the next one is 5. Right? So 5 is bigger than 2, so swap 5 up here and 2 back here. Right? We done, right? Still going up. Still we have 10. So now swap 5 to the back. 10, 7, 5, 3 to the front. 3, 2, 1. Perfect. Now where's 1? Compare 1 to 3. 3 is bigger. Good, stay the same. 2 to 3. 3 is also bigger. Stay the same. So now we swap 3 and 1. Right? It's going to be 1, 2, 10, 7, 5, and 3. Right? Because 3 gets swapped, it gets taken out right here. So now 1 and 2, same deal. 2 is bigger than 1, 2 go here. Still 2 go here, 1 go here. Right? Everything is stay the same. Keep rolling that, right? So then we take 1 out, I mean take 2 out, and 2 is now going to the back of this. Right? 10, 7, 5, 3, 2. And 1 is the last one, so in the next iteration it's just going to be like 10, 7, 5, 3, 2, and 1. So the whole time we stay in the same space of memory, and we just swap numbers together, right, to traverse them. So that's it. That's a 2-way to solve mass heap or min heap problem, right? For the mass heap, you swap the bigger number to the top. For the min heap, you swap the smaller one to the top. That's about it, right? So if you get asked to like, hey, how can you solve a min heap problem or mass heap problem, you can write it out like using this methodology method, right? Now let's take a look at the code that we have. You see, right? All of this is for reference, right? So on and so forth. I have it's not very nice, but you visualize the mass heap, right? Attributing the mass heap, so on and so forth. Visualize min heap and attributing the min heap, right? So yeah, how does heap sort work? Right? Heap sort use a mass heap to sort an array as an order in here for descending order, control everything, control step. First we'll build a mass heap, right? So descending order. And then extract elements while the root. So for we do the sub heap by one, effectively placing the last hit element at the end of the array. Find a position, right? For the heapify function on the root to restore the mass heap property. Repeat this process until the heap size is reduced to 1. Okay? High and space complexity, right? Okay, see this? Well, with high complexity can kind of mess up because the worst case scenarios can be O n log n, right? Because we have to swap a lot and we have to traverse all. But for the space complexity, it's actually awesome, outstanding because it's in place sorting, right? Which is we don't we use this algorithm for like we sort everything in place, right? In the same place, right? We don't need any extra space, right? Property of heap sort in play, right? Heap sort does not require additional storage, right? Sort right place. Well, not stable. Heap sort is not a stable sort, meaning it does not preserve the relative order of equal elements. Well, yeah, equal elements. That's really interesting. Consistent performance, like unlike quicksort, it can be regraded to O n to the power of 2, right? Within its worst case, right? Quicksort have a warranty O n log n. So quicksort, right, in the worst case scenario can be degraded to O n to the power of 2, where the heap sort is always like worst case scenario can be on O n log n, right? Time capacity regardless of input, which is pretty cool. Okay, when do you heap sort? Memory constraint, obviously, when we don't have a lot of memory, right, to perform sorting algorithm, you heap sort. Yeah, heap sort is suitable for situation where memory users need concern, warranty performance, right? You heap sort when you need a sorting algorithm with consistent high complexity for all input, right? Heapify using heap sort. Heapify is a function that ensures mass heap or min heap is properly maintained for the subtree, right? So the function I just performed for you guys right here, the in-place sorting is on a heapify function. And now we'll demonstrate them in coding, right? And that's the end of it. All right, so I have two versions of this heap algorithm, right? And they actually, the heap is really short, if you, like really short, if you can see that, right? There's not a lot of code on this, right? And well, I have a vector version and also have an array version, right? So not a lot of difference, but I do want to show you some, there's a big difference, that's right. Let's actually run this real quick to see what's the difference of this thing. Terminal. Okay, clean and clear. So that's cd to the structure. I think it's going to be chapter 17. If that's correct. Okay, so we have the heap array. Okay. Let's start with the traditional heap. Okay, type it in which line is got it. So again, it shouldn't matter if I'm using the wrong compiler, or not the wrong default compiler, which is C+94 or something. But yeah, as long as you change it to the standard C++, that should be great. Okay, so let's do a step try on this, right? To see what we do over here. Okay, I have using a W0 for index, right? 099, blah, 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 right? I have a vector, like, okay, integer, and data is like messy, right? Okay, I put the sort data. Okay. Before I output it, I'm using a heap sort, and I sort the data, right? And noticing I pass the data by value, right? If we pass it by reference, right, it won't work. Constant even work, right? So we tell, if we pass by constant reference, we tell the machine like, hey, I passing this, but you don't change it. Yeah. But to be sure, so I want to pass it by value. Okay, I'll put the sort data, right, skipping the W0 indexes. For ignite equals to data size plus I, and we display, hey, CL data I equals and another sample when we have data 03921 to display it, and we can see by our eyes that it's sorted, right? We have another sample, it's like, hey, we have more data, it's not sorted, and we pass it to our if sort function, and we return the sorting point, right? This step's done because actually eliminate my zero, right? So don't like that. Square. So, and display and line turn 0. Okay, now let's go look at the function here, right? So in order for us to do the heap sort, right, we have a couple of support functions, right? And then we can see it like plus a little bit. This. Okay, using them display standard. Okay, we have an integer get left child index, which is we're using this to get the children, the parent, right? Position, return 2 times position. Get right child index, return 2 times position plus 1. Oh, this thing is actually we have the parent and we try to get the child, right? And this thing is the get parent index, which is we pass in the position and we return the position divided 2, which is pretty plain in with coding. We don't have to explore or like absolute value, so on and so forth. Okay. And down here is also the view massive from sort unsorted vector, which is the heapify function, right? View massive. So basically, in view massive, we pass in the vector integers by reference and heap, right? So integer star index equal to heap size. So okay, so right here we pass it by reference, which is great at all, and pass it by value. It's actually passed by reference. It's pretty good. So we don't have to actually copy that to the memory, save by the log space, right? So in star index equal to heap size and divide 2, right? So in I equal to star index, I bigger than 1, we do the size I, and we call it a maintain heap, right? Which is pass in the heap and a heap size and I, right? So we maintain heap, which is cool. So the maintain heap is this thing right here, right? The maintain heap is taking the heap size and the position, right? So enter the left child index. Now we conjugate left child, right child, and we break last position, last the current position, pass it here, right? So if left child is smaller than heap, size and heap is left child bigger than heap position, right? Last position is going to be equal to left child modifying that. Otherwise, and same deal here because we want to make sure that we compare the left child and right child. This is not
Meow.
this is not because if you noticing when I do the drawing earlier, right? Even though we passed through it the first time, we compare it, but when we get to it, we got to compare it again, right? So it's not like you swap it and it's okay, right? So if you're noticing, when we swap this thing right here, right? We go to it, we swap, for example, uh, 3 and 7, right? But when we get here, right, we're still gonna swap it. If this thing is, if 3 bigger than, if this number is bigger than this number, right, we're still gonna swap it. Okay, that's the idea of it. That's why it's not a flow control. It's actually compare each of the elements, right, again. Okay, so right child is one if side, and if right child is bigger than if last position, then last position is right child, and then we swap it, right? So if last position not equal to this position, right, we want to swap, we're going to maintain masking, okay? Recursive calling again. Recursive maintain the masking property, right? So what we did, okay? So basically, if sort is going to call it a build masking, right? And then build masking is going to build it the first time. And later on, right, when we actually iterate through it and keep doing that, we're going to call the maintain masking, right? Build masking is this thing right here. Build masking to be the first time, right? And then we maintain the masking. Okay, maintain masking is also recursive. Okay, so that, well, yeah, you definitely we need to make it in 3 function like this, because only the maintain masking is the recursive part, right? Right? The maintain masking is the recursive one. The build masking and the insert is not a recursive. Okay? So, and remember every single time, right? So the for loop, right, it stands for this, right? The for loop is stand for each of the time we iterate through it. So 1, 2, 3, 4, 5, 6. Right? 1, 2, 3, 4, 5, 6. This is 6 times we iterate through it. Right? And we are creating this. Right? So this is a for loop. We iterate 6 times. And each of the time we recursive traversal to each of these elements to swap it. Right? So the logic fairly simple, but I'm pretty sure, I think in recursive 3 times like this, right? Usually they don't ask you to write a heap function. They ask you how you can use the heap function to solve a problem. What usually question on interview, like, hey, how can you use a heap function? What's the time complexity of that? What is the space complexity, and when you use these functions, right? To build something. Okay. Yeah. So that's the traditional heap. Let's check which is using a vector, right? Now take a look at this. This is a little bit more slow, close to what we're doing because it's our sample using right? This is closer. Let's see. Do different this makes. Okay. Oh, come on. I'm pretty sure that I would not have issued this because in this example we're trying to use some iteration on a vector, which is not available on older C++ compiler, right? So in this thing, we don't using any feature of the new C++. It's like very basic on C++. Okay, the sort array is 5, 6, 8, 9, so we can check and visualize and we see, oh, this is correct. Let's take a look at this. We have integer array, we initialize it with some like random number put on array, right? And we say, hey, what is the array size? We decide the array, this have size array, divide for size of array, x 0, right, to get the size. If sort array and array size. Okay, so this is full. This if sort function passing the array and the array size. And in this example, we're only passing the array, right? So that's the way. Okay, so take a look at this. Why different? And then we display it. Array and array size. Which is string array. So let's take a look at like string array, right? It's just like, okay, for the 8 array, same deal. Now take a look at the heap sort. Okay, the heap sort is taking 2 parameter array. We see the 2 arguments. We see the heap array. Now it is actually passing by value, right? And the heap size is size the heap size is array right here. Okay, view max here from an array. So for an I with heap size, I have to put the heap function. So a little bit different from this, where we actually just call the view max here. We actually just what we can actually put the thing in here, right? And still gonna have the same effect as the other one. We put this down here to show different. Like we build the heap first, and we actually traverse. So and sort it. The same thing. Call the heap define and extract element 1 by 1. Just another way to do it. So now take a look at it. Okay, so the time complexity of this heap function right here is gonna be 4. It's gonna be ON, right? Let's take a look at heap define. Because the heap define right here is actually reduce the size thing by half. Right? This thing is pretty sure it's gonna be like log n, right? 4 in I with the heap size of 2 by 4. It's about 2 by 4. Would reduce the size of the heap every single time. Okay, this thing pretty much have the same deal of the heap define function over here, which is maintain max heap, right? Instead of maintain max heap, we have something called heap define, which is closer to what we study, right? So large index equal to index. Yeah, in here we don't have no support function like, hey, find the left, find the right, find the parent, right? We just straight up like, hey, left child, that's going to be equal to 2 times index plus 1. And right child is going to be 2 times index plus 2. Right. Same comparison, same deal like over there. And on the swap and have to keepify. So over here, we also have the swap, right? And we have the swap. This is 4. Okay, perfect. So this one swap is a C++ standard template library swap. And this swap is belong to the C++, because it belongs to the C++ standard template library, it's allowed to overload many things, right? So in this example, it's swap, and you can literally see it's an integer, right? Even we didn't define this thing, right? It's a C++ tool, right? It's just automatically going and swap x and y, right? That's it. It have 31 overload, which tell me like, hey, this thing can swap integer, swap double, or swap object, swap whatever. And we didn't write this code, right? Standard, it belongs to the C++ that template library. So technically, I didn't write a swap for this. The reason we can do it is because we're using vector over here, right? Let's try to curious if we don't use this. It's gonna this. This is great. So it's also built baking the earlier version of C++, which is cool, right? I don't have to write a swap function here, which is cool. Let's take a look at the extract map real quick. So extract maximum. The heap array, extract map into a heap array, integrate stuff. Actually, I still want to use this. The reason we want to use this is because these are the swap that they have, right? So imagine this. The swap what they have is having 31 overload, and obviously the code is going to be way complicated as the swap that we have here. So we just want to use something simple, right? For our use case, this is all we have to do. We're using our swap instead of that swap. That's about it. Yeah, so I think that's the reason why I do it right here. Cool. If array size more equals 1, we return minus 1. Empty, if array size equals 1, then array size minus 1. So this thing should have if sake, so it's going to be 01 here. All this thing do is return the maximum element of if. Yeah. Or if you find in here again. Okay, so this thing, right, have a for loop and it's called a hippify in here. And a hippify is a recursive function, just to be over. Call this thing in here. So and time and log n. Right? This is for loop, have a recursive or n in here. This for loop is divide by 2, so it's going to be log n, right? Time complexity in this form. It's log n. But because we have a recursive function here, so it could be n times n log n. Okay, let's take a look at this. This is a while loop, right? If bigger than 0. One is saying bigger than 0. Then say 2. We do this side. Okay, right. Okay, right. That is extract. 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 Okay, extract map is have a time complexity of 50 think it's for one operation. Okay, Hipify, which know for sure is going to be ON. So this is switching magnetic right here. It could be have a time complexity of ON, right? So we have O log n plus ON. So it's going to be ON log n plus ON, right? So it could be ON log n because here, right? So this thing n log n is going to be bigger than ON, right? So we have plus, we just going to go with the thing that is bigger, right? So it really answer this thing have a runtime of n log n. And because it's swap in memory, so it's going to be have a space complexity. Okay, that's going to be like pretty much like interview question if we may have on a if function. Alright team, so I think that's all I have for you guys today. Is there any question? Check. Is there any question or anything to do today? Is it not clear or want to do something again? Yeah, so yeah, that's gonna be it, right? We get it done a little bit early today, but oh yeah. Hold on, before you guys go, I want to share something cool. I think this could be cool. So recently, right? Okay. Recently, like I learned, not learned, but I learned to do it at work for a period of time before. I also learned something called like IAC, infrastructure code, like something like we are using like YAML files, right, to set up the infrastructure on the cloud, right, for cloud-native application infrastructure, right? And also like why it's important, what we learn in this structure. There's something called the round robin round table, right? So pretty sure like the round table is using some sort of like data structure algorithm to route a request, right? So it actually depends on us as software engineer to say, hey, this thing has more priority and we want to route to, for example, this server, this node, right? We call it the node, do it that way, right? Node A, node B, and each of the node it can serve as a separate server, right? So specific from. So that's what I said. I want to show you guys. Really interesting because I also I have a setup right here. So over last weekend, what I did is like I set up my my workstation. I have a Windows Computer 64-bit SSD workstation, and I basically delete everything, and I set up it at a server. Right. So let's see. So in my server, I'm using Secure Cell OpenEdge right to log in, and I have a plugin here. If you guys are interested in this setup, I can teach you guys also. So basically, I can control my server, and I deploy my Kubernetes contain Kubernetes cluster, right? And it's not a full size Kubernetes cluster. But it's a Minikube, right? So I deploy Minikube on this application. So it have like 128 RAM, right? I have 64, but I plan to put like another 64 RAM on this server, and also like to see my home lab, right? So kind of like set up and play around with that, you know, to learn more about. So usually I've been cloud native developer, DevOps engineer, but I want to learn more about how can I, set up my own AWS sort of thing, right? Play around with that. So yeah, I think this can be interesting. Just yeah, and right now I'm in the server, right? So I'm just logged in the server. So wherever I go, I can communicate with my server to this, and this server is just like it's a Ubuntu server. So it have queue control, SSH, yes, code server on here. So it have no UI, right? So it's just a Linux server run on bare, not bare metal, but like on a workstation. Yeah, that's it. That's all I want to share with the team. So if you're interested in, let me know if I can throw some resource for you guys to set up the hub lab and so forth. Yeah, I have Michael K. Just set it up over this weekend. So yeah, team. That's it. Any question? Take care and I'll see you guys. And it's the first part. Oh yeah, for sure, Brian. I mean, like not even review, but
invited out to California for an all-expense-paid 2-day trip to test out the Canon R1, the company's latest flagship mirrorless camera. They put me up in a nice hotel, fed me lots of great food, beef jerky, Uncrustables, croissants, pistachios. You name it, we got it. It took a group of us to 2 different beautiful locations to learn more about the R1 and to get to test it out. I should have been a rally car racer. So cool. But as grateful as I am to get to go on these trips, as grateful as I am to be invited to go on these trips, saying yes to them is a really tough decision. Because money and experiences have a real effect about how you feel about a product or a brand at large. And I've just been thinking a lot about my personal ethics as a creator. So I want to take a moment to walk you through my decision-making process. And although my process might evolve and change as I grow, I think it's important that we set some ground rules so you know what to expect around here. I usually take it outside, so it's a little different, but I really think it's important. So let's start with brand deals. I think that most folks understand that brand deals are a major way for creators to make a living, and you've seen 2 of them on this channel already. But I have a few rules for what I say yes to. First, I like to personally vet a company to make sure that I feel comfortable with my audience spending their money there. And second, you cannot buy a review of your product on my channel. When a company buys ad space on your channel, it usually comes with strings, like language that you have to use and approvals you have to get. And if a company has any level of control over a review of their product, then there's no way as an audience that you are getting an unbiased review. Not to mention that money just carries energy. For example, if this water bottle company pays me to review this water bottle, say it's about $10,000, I'm gonna feel pretty damn good about this water bottle. It just got me $10,000. And then if I have to send this company my video before it goes live, and they have to approve it, well then I'm gonna work towards an edit that they're going to approve, right? Anyway, no paid reviews on this channel, that's just... Okay, let's talk about brand trips. At the beginning of this video, I was talking about how I got invited to Palm Springs on Canon's dime, and I went on this trip because it was the first opportunity Canon has given me to use its latest flagship camera, the R1. And using this camera informs a lot of my reporting on all other cameras. It was also a great opportunity to meet some really incredible photographers and get to learn from them. But I did walk away from this trip with a new rule for myself. I will not be reviewing the device that the trip is centered around on these trips. Because 1, this company wants you to have a good time, and 2, they set you up for success. They bring you to beautiful places with models and professional athletes and professional drivers. You quite literally can't take a bad photo while there. So all reviews are going to be in my space, on my time. Brands on time, this was super helpful. But I often say no to these trips because I don't really need to be in, I don't know, London to learn about a smartphone. Because it's not about speaking engagements, I have to do a lot of these. And although they are typically held by companies that I cover, I plan to say yes to a lot of them because 1, I want to get better, 2, I want to meet all of you folks, and 3, typically these events are not about specific products, and if they are, I won't be there talking about them. An example of something I'll say yes to is this week. Actually, Sony is hosting an event here in New York City, and I'm going to be doing a talk with Casey Neistat at it, which is so exciting and cool, and I can't believe that I get to do this. But yeah, we won't be talking about cameras directly. I will not be endorsing Sony products. I'm there to have a conversation with Casey about being a creator in front of other creators, and yeah, I'm super looking forward to that. So now let's talk about gifts. I am sent so much swag and free stuff, and I'm loaned gear, and sometimes I really worry about the environment and how much plastic and packaging is going into these things. But when I say yes to receiving something, I also always say this. I cannot promise coverage, and if I do decide to talk about something, I'm going to say whatever I want about it. That one's pretty plain and simple. If you send it to me, it's out of your hands now. Okay, that's everything I can think of now. Let me know down in the comments if there's anything else that we should talk about. I'm happy to chat. I also said this in the beginning, but I'll say it again. I'm growing and changing every day as a creator, and there's a lot of gray area in this world, and I know that at some point I'm going to do something that you disagree with. But I hope that when that happens, we can have an open dialogue about it. Yeah, because we're all just people.
times, and going to start out. Where Democrats seem to be understandably disorganized, vague, confused, and this is understandable. And we're searching for a narrative. Let's just say that word, narrative. In other words, we need a story that we can put forth to the American people to get them to understand how rotten and despicable people are in the opposition. All of them, a lot of people in opposition are. And of course, I'm like anybody else, still feeling the effects, talk to people.
We've learned new information about former Nebraska Senator Ben Sasse and his resignation as University of Florida president and his spending during his 17-month stretch as U.S. president. Nebraska Republicans were shaken when Sasse announced he was leaving the Senate to take a job at the University of Florida in 2022. In his last time in D.C., Sasse served as president of Midland University in Fremont. According to the Alligator.org, a new media outlet that covers university news, Sasse tripled his office spending from nearly $6 million to $17 million, putting money towards things like consulting contracts and high-paid positions for previous GOP colleagues. He hired 6 ex-Senate staffers and 2 former Republican officials, which the Alligator says accounted for nearly 30% of his office's spending. One example is James Wegman. He was Sasse's former Senate communications director and hired to be U.S. Vice President of Communications.